In this podcast, we're going to talk about how the structure of amines contribute to the physical properties of amines, such as boiling points and solubility. All right, most low molecular weight or short carbon chain amines are soluble in water, and this is due to the fact that nitrogen and hydrogen make a hydrogen bond. So there are weaker hydrogen bonds. As you increase the molecular weight, or as you increase the length of the carbon-hydrogen chain and you increase that nonpolar region, the solubility of your amine is going to decrease. So amines are going to be more soluble than corresponding alkanes because they do have the nitrogen group that is able to hydrogen bond with water, but their solubility is going to be lower than corresponding alcohols. And the reason for this is because we have, in both cases, we have hydrogen bonding, whether it's between oxygen and hydrogen or nitrogen and hydrogen. However, the difference in electronegativity between oxygen and hydrogen is a greater difference, and therefore you're going to wind up with a more polar bond. Whereas the difference between nitrogen and hydrogen in electronegativity is less, so it's not going to be as strong of a hydrogen bond. Comparing amines, their boiling point is going to fall above ethers but below alcohol. So there is some hydrogen bonding there. It is able to keep those molecules, those amines, to hold them together better, but it's still not as strong as the alcohol, which has a hydrogen bonded to an oxygen. Amines typically are responsible for very sharp odors. If you think about if you use ammonia to clean your house, it has a very sharp odor, not something that you would want to do anything more than waft. And as we've talked about in previous podcasts on amines, we find them in medications such as Benadryl, citrazine, methadone that we've talked about previously. All right, so looking at a one carbon amine, we can see that a nitrogen and hydrogen are going to have polar bonding, and the dipole is going to point towards a nitrogen. It's more electronegative, so it's going to take on a slight negative charge, and your hydrogen is going to take on a slight positive charge. That slight positive charge on a hydrogen of one amine is going to be attracted to the slight negative charge on another nitrogen of another amine. So this attraction between these slight charges is what creates that intermolecular hydrogen bonding. And again, hydrogen bonding is the strongest type of covalent bonding, so therefore they're going to be held tighter together. They're going to have higher boiling points, higher melting points than, say, just an alkane. But the difference in electronegativity between the nitrogen and hydrogen is less of a difference than what you would see between oxygen and hydrogen. So therefore, alcohols would have a little bit stronger hydrogen bond holding those molecules together. All right, so let's compare ethers, amines, and alcohols in terms of boiling point. So an ether is only going to have dipole forces holding those two diethyl ethers together. So it's not going to take as much energy to separate those two molecules, therefore the boiling point is going to be lower. As soon as we introduce a nitrogen bonded to a hydrogen, we have hydrogen bonding. So that's a stronger type of intermolecular force. It's going to hold those two 1-butanamine molecules tighter together, and it's going to require more energy. So therefore, the boiling point will go up from 38 degrees Celsius to 78 degrees Celsius with the presence of that hydrogen bonding versus just the dipole bonding. If we were to compare this to an alcohol, same chain length, it is also a 4-carbon alcohol. Because you have an oxygen and a hydrogen in your hydrogen bonding, that is slightly stronger than the nitrogen and hydrogen, and therefore it is going to take more energy to pull two of these 1-butanol molecules away from each other so that one could escape as gas. All right, this plant you're looking at is called an angel's trumpet. And angel's trumpets are plants that have the amine scopolamine in them. And scopolamine is toxic, so you don't want to go eat this plant or these flowers. However, we have found if we can take some of this scopolamine and put it into a transdermal patch, and we stick it on the skin, and usually it's stuck right behind the ear, a little sticky transdermal patch. It will release minute doses of scopolamine, which are not toxic, but they're actually very helpful for use in treating nausea and vomiting associated with motion sickness. So if you were to go on a cruise, you might have to purchase or be prescribed scopolamine transdermal patches. It doesn't have to be just for motion sickness. Scopolamine patches can be used also to treat any nausea and vomiting, perhaps in a hospital setting where patients aren't tolerating the prescription drugs they're on. This is a good way for them to be able to not vomit while being on drugs.